Let me introduce Professor Jorgensen from University of Iowa, who will be talking today about harmonic analysis and reproducing kernel properties for singular measures. Palle, the audience is yours. Again, please, everyone, mute yourself during.
Thank you very much for the kind invitation, and thank you very much for everyone to log in. And I'm very honest to get such a distinguished audience, so I hope I can live up to it. So from the title, you might have guessed that it has something to do with work I did with Peterson some time back, dealing with creating Fourier expansions on certain self-similar fractal L2 spaces. However, the main theme here is actually more recent work, which again is motivated by the same theme. In other words, the desire to create Fourier expansions in L2 spaces for a class of measures that have self-similarity or have some other properties that are consistent with the structure of singular measures like this. And this other work here is actually much more recent. And I want to stress that the main results that I'm going to report today will be joint work with two co-authors, Eric Wepper and John Herr, H-E-R-R. And so I'll cite those papers in a moment. Right, and then also some joint work with another co-author, Finn Chiang, and so there'll be the two co-authors, Eric Wepper and John Herr, and another co-author, Finn Chiang, and that deals with extensions of the basic idea of doing harmonic analysis in a wider context. And so the main new ingredients that comes into the game is certain classes of kernel spaces, and I'll talk about those. And one of the problems is inverse problems going from spectrum to geometry, and in that direction, you'd be interested in identifying fractal scales. And so that's that. The picture in the background illustrates some kind of structures that you want to do harmonic analysis on. And this is generated by certain simulation with Monte Carlo, but the main purpose is actually decoration. All right, so that's that. This is the abstract, and the abstract just writes out in words what I said. And so these singular structures, some structures that's generated by algorithms, that it could include networks and limited networks. Networks could be social networks, electrical networks, neural networks. Take your favorite network. We'd like to do harmonic analysis on them or on limit structures created from them. And ideally, we would like to do some kind of Fourier expansion for those that you can't do unless you introduce some new points of view. And the new point of view here would be twofold. One is a certain kind of positive definite kernels and some kind of boundary analysis. Or maybe I should just, for the sake of dictionary, when I said a positive definite kernel, then in the literature, some people just say a positive matrix, because if you have a function in two variables, you can think of the first variable as row and the second as a column. But in functional analysis, usually you call them positive definite kernels, but sometimes I'll just call them matrices, and that's fine. Okay, and so that's the abstract here. And now for the papers that are at the basis of the slides here. And the first two papers is joint work with a colleague in Israel, Daniel Alpay, only he isn't in Israel anymore, he's in California now. This is work that does harmonic analysis of a class of Gaussian processes computed from the kind of measures that we do harmonic analysis on. And so those are two early papers here. And then the next are the papers with my, those are actually the papers that are the main source of the theorems in this talk here. So with the Erik Weber and John here. And one is the first paper, and it came out in Journal d'Analyse Mathématique. It's the main journal in Israel, and it has a French name. And if I had time, I could explain something about the history of Israeli journals, but I don't. So just if you, yeah, right. So there's some French names here, and don't worry about it. And the other one is, so when I got interested in the subject here, I somehow managed to get the attention of Bob Strickert. And so since my work on harmonic analysis and fractals, I've been invited many times to Bob Strickert's conferences on fractals and analysis on fractals. And the last one generated some invited papers. And so the last one on this list here is an invited paper with my two co-authors, Weber and Hill. And it's in a beautiful book, I should say, in World Scientific. And if you haven't seen it, it's really. I mean, I like, of course, the paper that we have, but I also learned a lot from the other papers in that. And that's right. So we're actually supposed to have an in-person conference again, but because of COVID, it got postponed, the wonderful fractal conferences at Cornell University. So what's next here? The next is CBMS, where I gave 10 lectures, and it was initiated by my friend Erik Weber, and I'm very happy about it. And it took place in my neighbor university where Erik Weber is. And then there's a first paper with Sean Peterson, and then something on stochastic processes, and then a recent paper with Fen Chang. And then for the point of view of a more general class of kernel spaces, we actually very much inspired by kernel spaces invented by Lohr and Schwarz. They were in two papers, and the second one here is also in the Israeli journal, Journal d'Analyse Mathématique. And it was back in the time when the French was dominating as a language in mathematics. So it's a long paper by good old Lohr and Schwarz. And noyau reproduction is reducing kernels, but it's reproducing kernels in a sense that's more general than the one that you might be familiar with. So I'll stress that feature as well. And the last one here is actually a comment of Strickert to the paper with Peterson. And the comment has to do with the different approaches, wavelet approaches, operator theory approaches. And Strickert wanted to get in print a wavelet approach to these fractals. Okay, all right, so here we go. This is the main theme here. So the measures are typically singular measures, and the motivation comes from the class of singular measures that arise as what's called iterated function system measures. And so those are measures that have a self-similarity coming from an iteration of scales. All right, so the iteration of scales would also give you resolution, so it fits into the way we think about multi-resolutions. So that's that. Okay, and the next one here is a super quick summary of some of the stuff in my paper with Fen Chang. And what it is actually referring to the good old conjecture of Fourier. The conjecture of Fourier was as follows: take Rn and take an open a bounded domain, and then ask for an orthogonal system of Fourier exponentials. So an orthogonal system of e to the I lambda dot x when lambda runs over some subset of Rn. And if you can get an orthogonal system like that, we say that we have a spectral pair, the set and the spectrum. Now that turns out to be quite tricky to decide, and the conjecture is that it's equivalent to having the set omega tile Rn by translations, and the conjecture inspired a lot of wonderful work. It's not true in dimensions 3 and higher. it's actually still completely open in dimension 1 and 2, and so it's still a big inspiration. So the approach that Steen Petersen and I took was that you can define, if you look for this, then you can instead define the problem locally. So you can define a positive definite function that's only defined locally, and then you can ask for extending it to all of Rn. And so that extendability turns out to be equivalent to an affirmative solution to getting a spectral pair from a given open set. So that's what all of these keywords here refer to. Okay, so now I'm ready to go back to good old Lewin-Schwarz here, and what it is a more fruitful approach to reproducing kernels, and it is developed in Rn, but in the slide here I'm just writing it for n equal to 1, but everything I say here would also work if n is bigger than 1. And so the idea is that you want a tempered distribution, and then you want these convolutions with test functions. For some purposes, the compactly supported functions would be good enough for test functions. For other purposes, you might want Schwarz or C infinity, etc., etc. But when I said test functions, then I want to be flexible about which choice I want to make for test functions. And then, here in the last line, it should be phi tensor phi bar, not convolution here. And what we have here, it's a very, very natural thing. We want to create a Hilbert space by completing these convolutions here. And we want to complete them with respect to this, this pre-Hilbert structure here. And then we get a Hilbert space. And that's what we mean by the generalized Köln Hilbert space inspired by Lewin-Schwarz. And so it turns out to be a very useful tool for analyzing Fourier expansions for L2 of mu. And why? Here's why. If you have a positive definite tempered distribution F like this, then you generate these convolutions, and so you get a system of functions, and you complete that, and then you get a Hilbert space that are right with the script H sub F. And then from the definition we have here, that if the positive definite distribution F is the Fourier transform of a tempered measure, then this defines an isometric isomorphism of H sub F onto the L2 space of the measure mu. It's actually onto. So it's a way to create a harmonic analysis tool for L2 spaces. So it's exactly the kind of tool that is going to be the focus of what I want to talk about today. Now, if you're not used to tempered measures, think of this one here as in the bullet point as an example of a tempered measure. And so why do you want it to be tempered? Because then you can make sense of these candidates for the norm squared in this more general kernel Hilbert space. And you can see the right-hand side here is sort of an example of a Green's function for an elliptic PDO, if you like. And whenever you see a hat here, that will just be the plain vanilla Fourier transform applied to test functions. So if we have test functions, there's no difficulty applying Fourier transform to them. And if you have tempered distributions, then you just define the Fourier transform of a tempered distribution by dualizing the Fourier transform of the test function. So that's standard lingo from good old Lewin-Schwarz. And so the point of view of realizing Fourier transforms in a suitable L2 space here is actually also relevant for the plain vanilla approach to the localizing signals in an interval. For example, the interval from 0 to x, if you take the bump function there, then the Fourier transform would be the sinc function. So on the right-hand side, you actually have the absolute squared of Fourier transform. But the thing is, the absolute squared of the Fourier transform is calculated in L2 of mu, where mu is a measure to be studied. And so if we do this one here, then we get a certain family of functions R mu, and they would represent variances for the kind of Gaussian processes that are associated to these measures here. And the next one would then be the inner product, and that would be a covariance. But the idea is that you have to get such a Gaussian process, and the only way you can do that is to create probability spaces, and the probability spaces would be created as L2 spaces of a cylinder sigma algebra of subsets of S prime, where S prime are the temper distributions. The last line here is a property of such Gaussian processes that we call, and this is work with my colleague Alpay, where we call that a stationary square increments. Now the process is not stationary in the usual sense of Gaussian processes, but the square increment is stationary because the square increment is a function just of the difference here. So those are important classes, and they are directly connected to the class of measures mu that I plan to study here. So the next one here is from kindergarten. And so in kindergarten, you learn to do the Dirac comb and the Fourier transform like this. And so the Dirac comb is just a Dirac function localized on the integers as a subset of the real line. And we know from Lorenz-Watts that we can happily Fourier transform, and then we get a positive definite temper distribution, and that's 1.2 here. And then the isometry that I talked about here translates into what we learn in kindergarten about Fourier expansions for L2 functions on a period interval. So that's equation number 1.3. So our purpose here is to imitate that kindergarten stuff here for more general singular measures. Okay. So the first one is the first one that comes to mind, at least in the circles that I often talk to, is the Cantor measure you get by dividing by a scale number 4. And then you get a measure whose Hausdorff dimension is a half. How do you understand that measures? There are at least 3 popular ways of doing it. You can think about the left-hand side as an operation on measures, and then you can think about mu4 as a solution to a fixed point problem. And so that's one way. You could also say that you can Fourier transform a measure, and then you can use equation left-hand side here of 1.4. And then you get a factor out like this, and then you can iterate the Fourier transform and you get an infinite product, which would be a continuous positive definite function, and therefore by Buckner, that's the Fourier transform of a unique measure, and that would be the measure mu4 that you have here. Mu4 is also known as an iterated convolution measures, if you like Bernoulli convolution measures. So it's an old friend, and everyone has his or her favorite way to think about these kind of measures. But what Steen Petersen and I did back then, which Bob Strickert thought was really cute, was that we did a Fourier analysis on that. So here you have a fractal in the small where you keep scaling down by factors of 4. The fractal in the large is where you inflated by powers of 4. And the corresponding Fourier series we think of as lacunary. And I'll explain that in the next slide here. I think that's all I want to do on this slide here. So there are the lacunary thingies. And so the thing that happens for this mu4 is that you have a Fourier expansion in terms of the Fourier exponentials E lambda, where the points lambda are in such a subset of the positive integers that have this lacunary properties, so that you have gaps in the size that's the order of powers of 4. Of course, you could do that in other kinds of inflations, and then lacunary Fourier structures is when you have gaps in the spectrum that are powers of some expansive mapping. And so the those are, you can see that they're pretty sparse, but still what our theorem with Peterson is that that you can get an honest Fourier expansion, so that's that. One of the things I learned later when I got to know Strickard, but he actually has a beautiful publication that these kind of Fourier expansions have a more localized structure. So one of the things he proved for them was that's something that should surprise you if you remember what you learned in kindergarten about Fourier expansions of continuous functions. They don't always converge. But these kind of lacunary Fourier expansions for continuous functions do converge. And that's because they're more localized. So keep that in mind. Then that raises, I'm going to now go to a wider setting that allows us to do this Fourier expansions for a big family of measures mu. And so the question of which one of these measures then also have the property of having good Fourier expansions for continuous functions is a good thesis problem for a PhD student. Okay, so here we have again a Dirac comb, and again, so you take the sum of the Dirac at the points in this lacunary set, and the Fourier transform would then be the sum of the corresponding Fourier series. I often think about why it's called a Dirac comb. And if you comb yourself with this lacunary Dirac comb, I think maybe that would be like a hippie hairdo. I'm not sure. Okay, but the thing that we learn from this one here is that that we get then that this Schwarz kernel space here again would be isometric isomorphic to L2 of this measure here, but that's because we have an orthonormal basis. So what we will see is that we could still get this isometric isomorphism here, even if we don't necessarily have orthonormal bases. And that would be a key tool in the machinery that that Eric Gruber and John Hare and I developed for more general Fourier expansions and inverse problems. Okay, so this one here is just a reminder that you might have seen positive definite functions in the definition. That's the last line here. And so I just want to point out that if you should have a positive definite function, then the two definitions of the positive definite property would be equivalent. And but I'll be concentrating now here of the one in the sense of Lorenz-Schwarz. And so that means that you start with a tempered positive definite distribution, and then you create a function, then you create a distribution in two variables by looking at x minus y, and then you let that distribution act on phi tensor phi bar, or on phi tensor psi bar, if psi is the second test function, and then you get a positive definite semi-inner product, and you complete, and that's the Hilbert space that we want to study. And we want to study when that Hilbert space is isometrically isomorphic to an L2 space. Here's a summary of the Bachner versions. Here are the two versions, the one for continuous functions that gives you bounded measure, the one for tempered distributions that gives you tempered measure, and the Bachner applies in both cases. And here is the reason for why we call this a reproducing Hilbert space here. It's because when you create a Hilbert space of distributions like this, then you can translate them by different amounts in x1 and x2, and then you can create an inner product here. And the idea is that that inner product on the right-hand side should be that distribution that we talked about. And so in the paper by Lorenz-Schwarz, this is made precise, and that's why we call them reproducing kernel Hilbert spaces in the sense of Lorenz-Schwarz. And what you also see is that the functions that we complete, you can think about as convolutions, but this would be convolutions between test functions phi and tempered distributions f. And we also remember from our distribution theory course that a convolution of two things preserve the best property. So phi tensor F would again be a nice test function. And so we complete these nice functions and get a Hilbert space, and that's the Hilbert space we want to study. But in particular, we have, since we can translate these temper distributions, then we get unitary representation acting on these reproducing kernel Hilbert space. And so that's what I'm saying in the left slide here. And such a unitary representation then has a spectral measure, a projection valued measure, and that would again be a key tool in harmonic analysis for the corresponding measures, because if F is positive definite, then it is a Fourier transform of a measure, as say in the second slide here. But what is the second column here on the top? I just want to make a connection to these Gaussian processes. So the expectation of e to the I dot, that's actually treating the dot as a variable in S prime, and the expectation as an integral with respect to a probability measure on the cylinder sets in S prime. And so such a probability measure exists because the right-hand side here is a positive definite function on S. And so that's one approach to generating these Gaussian processes. And you'll notice that in the exponential here, we have precisely the Fourier transform of the test functions integrated against one of the measures we want to harmonic analyze. And so that's that. And so this one here is then more details about the connection between the kernel tools, the boundary tools on the one hand, and L2 mu on the other hand. And again, this is very directly from my work with Erik Weber and John here. And so here to begin with, we specialize to measures that are supported on a compact subset of the real line. The reason for this is that we want to use kernels on the disk. So if you have a measure supported on a compact subset of the real line, you can rescale so that the support of the measure winds around and sits on a circle, and you can treat the circle as the boundary of the complex disk. And so that would be a key approach to how we will be thinking about these things here. And so this is then summarizing two questions, and it fits in the way we think about harmonic analysis and inverse problems. And so if we start with a geometric problem, we want to create a positive definite kernel, also called a matrix. And we want to do the case of measures with support, compact support on the line. So we can think that as the boundary of a complex disk. So we would then look for the reproducing kernel Hilbert spaces to be contained in the Hardy space. The Hardy space is the one from kindergarten from 3 slides previous. And so that's that. And so the question of studying subspaces of the Hardy space like this connects to work by also many, I guess, Alpi and I guess his collaborators, and Debange spaces, and so on and so forth. And so Hardy spaces are also, I guess, Don Saracen writes in the introduction to his book, although I spent most of my life in the complex disk, I've now later on taken an interest in going to the boundary. so that quote from Don Saracen would fit what we're doing here. Okay, so if you have such a kernel sitting inside the Hardy space, you want to understand the corresponding measure. If you have a measure, you want to understand the corresponding kernel. So there's a duality like this, which would be a recurrent theme in what we'll be talking about here. And so that's all fine. And so this one here is kindergarten for the Hardy space. So you can take the first line as a definition of the Hardy space, and then you can take the second line as a practical practical realization of the functions in the Hardy space H2 as power series like this with coefficients in little 2, and then Fattou's theorem is saying that they're the same. Fattou's theorem says that a function in the Hardy space H2 has a non-tangential limit as you go to the boundary, pointwise almost everywhere, and the L2 norm calculated from Lebesgue measure on the boundary function agrees with the Hardy norm, or the Hardy inner product agrees with the inner product from the L2 space. So what we're going to do now is imitate this, but the main thing is we're going to replace the Lebesgue measure with the kind of fractal self-similar measures that is the center of our attention. So instead of factorizing kernels in this baby way here, we want to factorize kernels in a more sophisticated way, where the measures that go into a factorization are allowed to vary. But if you just go to the baby Hardy space, then you know that the kernel that reproduces the Hardy space H2 is also known as a Sager kernel. And obviously you can replace one of the variables in the Sager kernel with a Fourier exponential, and then you can integrate there, and you see then that the Sager kernel factorizes like in equation 2.2, but we want to do that for other measures. And so the other measures, mu, that allow factorizations would then be studied in duality with the corresponding kernel. So if you have a kernel, there might be measures that factorize it, and corresponding, if you have a measure, there might be interesting kernels that create a factorization for it. And so that's the duality approach that we'll take here. And this one here is the definition of the most general positive definite kernel, also called a positive matrix. And the general theorem predating Lorenz-Schwarz is that there's always a reproducing kernel Hilbert space, so that such a kernel here reproduces the value of the values of the functions in that reproducing kernel Hilbert space. But here we're going to look at a different kind of reproducing. So what we like to do here is that we would have kernels defined on the disk, and we will think of the interval as a boundary, and the disk wind the interval around on the circle, rescaling the factor with a factor 2 pi. And so then you could ask for this kind of factorization here. And so if you start with a positive definite kernel on the complex disk, it's not at all clear what measures factorize. You might imagine maybe then there's some positive definite kernels that don't admit any factorization like this with a measure on the interval here, in other words, with a measure on the circle. And actually, I'm not sure we have settled the question of whether M of K is non-empty for the most general K, but we'll be interested in the measures mu that satisfy 2.3, and the measures mu that satisfy that we call MK. And so we'll have a lot more to say about MK, and similarly, starting with the measure mu, we will have a lot more to say about script K of mu, and the correspondence between them would be a new kind of duality. I saw from the list of participants that every one of you probably saw frames in kindergarten as well. And so here's the definition, and it refers to a Hilbert space. And if you have a sequence of vectors in a Hilbert space, then and if you have two constants A and B, and if A is positive, then you say you have a frame and a frame expansion. And if A is equal to B is equal to 1, call it a possible frame. And if you have such a frame here, then Xn, then there's a dual frame, so that every vector in H can be realized this way here. So I like to think about this as a generalized Fourier expansion. And for the formulation of frames, we have duality. In other words, you can think of Xn and Yn symmetrically. So if you have 2.5, then you also have the corresponding thing where you flip the role of the Xn's and the Yns, and that's all fine. And then, right. and the canonical duals as well. Now, then the next tool here would be maybe look at 2.6 and 2.7, but I like you to start with 2.7 and start with one of your favorite measures in the unit interval. And so that's the one that we want to study here and think about how to create the kernels corresponding to it. And we want the kernels to sit inside the Hardy space, et cetera, et cetera. But another thing we remember from the baby harmonic analysis is that there's a bijective correspondence between inner functions on the one hand and singular measures on the other. And so in 2.6, we have normalized the Cauchy transform. And so in the denominator, you could think of that as C of mu on the constant function 1. And C of mu on the constant function 1 is actually closely related to that inner function we talked about. So 1 divided by this C mu of 1 is actually 1 minus B, where B is the inner function corresponding to a singular measure mu. But you might have some measures that are not singular, in which case we would have B in the ball in H infinity, but we'll mostly study singular measures, and they would then correspond to inner functions. And so in our work, V plays a much more important role as does C. So V is the normalized Cauchy transform. And hidden in the denominator in 2.6 here is really the inner function, because the quotient here is the unnormalized Cauchy transform times 1 minus B. So keep that in mind. So that means from that you see immediately that V mu of F maps into the subspace of Hardy space that's usually called HB in the de Branche Donald-Sørensen terminology. Okay, so that's that. So I don't have time to go into all of that. And I want to now introduce a new workhorse in the analysis of my work with Wijnbaan here. And that's what we call a Kaczmarz algorithm. I'd say that it's motivated by one of the early versions that's named after Kaczmarz, which is the one for in linear algebra, but we want to do it in an adapted setting that fits what we're doing here. And obviously what we're aiming for is a Fourier expansion. And so we could say that, what about looking for a Fourier expansion of the complex Fourier exponentials here with lambda running through the positive integers, including 0. So in subscript 0 here, 0, 1, 2, 3. So what about aiming for creating a Fourier expansion for every f in L2 or mu when we have one of our measures mu with a support on the interval? That seems like a realistic thing. Well, obviously, since the En functions do not satisfy an orthogonal system, the En functions are not even frames. In fact, Fourier frames for these L2 spaces are really, really difficult. And most of the obvious questions you could ask yourself about Fourier frames are open questions, and serious people have struggled with them. And so what we do is that we want to apply a certain Norbert-Wiener filtering to the candidate for Fourier expansion. So the candidate for Fourier expansion are the E functions. So the En functions is when lambda runs through the positive integers, including 0. So what do we do for these En functions? We stick them into the inner product from L2 or mu. And so this inner product is also the Fourier transform mu hat of the difference between the indices N and I. And so that's a Gram matrix corresponding to mu. So what you're seeing here, and if the indices N and I are equal, then you have a 1 if you normalize the measure. And so you have a Gram matrix with 1 in the diagonal slots. And so I put down that in the bottom triangular place in an infinite matrix. and then I do the inverse of that. And then you have to worry about whether that's legal or not. And that's what we do in our paper. We get that it's legal to the extent that we need it. And so that means that if you have gram on the G system, you get an E system. So if you do the inverse gram on the E system, you get the G system. But the inverse gram, so that will just be this one here. So that would really just take the fixed n, you're just tracing it back for the frequency n-1, n-2 down to 0 here. So that's really just a fairly straightforward Fourier filter that you apply to your Fourier frequencies. And so what it says is that we can create such a Fourier filter so that every function f in L2 or mu will then have such a filtered Fourier expansion as 2.9. That will be convergent in the norm of L2 or mu. That's our first theorem, and would have pointwise almost everywhere, and other notions of convergence for these generalized. Okay, so this would then apply to a much wider class of measures mu, much wider than the particular classes of iterated function systems measures that are. So by the way, I should say that here I'm stressing one dimension. You could ask the same questions in higher dimensions, for example, Sierpinski structures in the plane, Sierpinski structures in 3 dimensions, etc., etc. And much of what we say here, we have also extended to higher dimensional fractal structures, but I'll still concentrate in what I say here on structures that can be realized on the line. So this is kind of the main, one of the main theorems here, and so I've explained that with a lot of hand waving, and hopefully I'll get a chance to fill in some technical details in place of the hand waving, but we'll see how far I get. Now let's return to our old friend. So you start with a measure mu, and you create the corresponding L2 mu inner product, and that's what you see in 2.11. And then you take the monomials, the complex monomials here, and then we saw that the normalized Cauchy transform takes you into the subspace of the Hardy space, and that's called H or B, where B is the inner function, and that's in the Barnes notation. And I don't have enough time to explain the Barnes. Here's what that means in more precise terms. And these more precise terms in our work, we often call them, we make precise what we call an Abel summation. So an Abel summation is if your sum is not good enough, you rescale it so that it's good, and then you take your limit of your scaling. So we scale it here by r to the n when r is smaller than 1, and then we let r go to 1. And if we're lucky with this, we say that we're successful with an Abel summation. And so to be precise about the Fourier representation of the functions f in L2 or mu, I can say that we can make a precise Abel summation formula with the use of our Cauchy transform v mu, and so we're sitting inside the branch subspace of the Hardy space where we do this. But then you also see that, what happened there? Then you also see that v mu takes you from L2 or mu to the corresponding subspace of the Hardy space, and it's invertible. So the inverse takes you in the opposite direction. And so one of the pieces of this theorem is that the inverse applied to a function in that Hardy subspace would then be a function in the L2 mu space realized as a boundary function. And so you could see that our transform v mu has the features that you would want for a spectral transform. So that's the part that I want to illustrate with my hand waving summary of our results from 2.7. Okay. And 2.8 is again, I can only have time for hand waving. Now, the branch theory does give you kernels for these subspaces, but what we would like to do is we would like to have it computational, and the G functions are the ones that come from our algorithm. So we want a formula for our kernel of the subspace corresponding to mu, and that's the one that's given by the inner function. We want that expanded directly in the language of our algorithm. And so our algorithm gave us the G system, so the Gn functions, and the Gn functions form a possible frame in L2 or mu. Now, it's not exactly a Fourier frame, but it's as close as you could get to a Fourier frame if you're happy with Fourier filters. And so we have created such a Gn system. And then what we show is that the kernel for the subspace of H2 is given by such an explicit formula here. So that would be a formula in two variables from the disk, conjugate in the first, so conjugate and leading in the first and leading in the second. And so again, a direct connection between mu on the one side and spectral data on the other side. And part of the spectral data is such a kernel here. And so in the language that we introduced earlier, we have that this kernel in 212 belongs to K or mu, or said differently, mu belongs to M of that kernel. And so remember, the meaning of this was that you can factor the kernel in 212 through an integral with respect to mu, as I explained in the first slide. All right, so that's that. The next one is mainly for operator theories who have fallen in love with, the Wold decomposition. Actually, Wold was a Swedish mathematician who worked for an insurance company, and he developed the kind of stationary processes, but the stationary processes gave rise to isometries, and they caught the attention of Helmers, who rephrased good old Wold in the language of isometries. And so obviously multiplication by an inner function is an isometry in H2. And so whether you prefer the language of one of the Swedish pioneers or the language of Helmers, you get that Wold decomposition is such an orthogonal expansion here with powers of the inner function. And the coefficients lie in the de Branch space. So the de Branch space in this case here is just the orthogonal complement of BH2 inside H2 for functions in H infinity that are not inner functions. You also have a de Branch space, but more complicated. But this one here is just the baby version. And so the reason that I mentioned this is going to follow in the next. By the way, if I have to choose between the two versions of Wold, I prefer my Swedish ancestor. Okay. Now, if you have a function in that subspace and you go to the boundary and create the boundary function, then you get the same for whether you put in B or not. But the main thing is that if you take the de Branch subspace and you multiply by powers of B, then you get such an orthogonal expansion, and that expansion gives you all of the L2 space, and that means that you get you get dense subspaces, each one of which gives rise to a kernel subspace of H2. And not only that, you can take a finite sum corresponding to your favored choice of subspaces V0, V1, and so on, with corresponding kernels, and then do sort of a truncated version of the Wold. And then you get a corresponding kernel like this. And that kernel would be in script K mu. And so you get a whole bunch of kernels in K script of mu for any one of your favorite singular measures mu. All right, so that was that. And this one here is a little bit different from the one I mentioned before, because the one I mentioned before, remember, said start with a singular measure here. Yeah, I don't. Here I just say start with a Borel measure, normalize and so on. And start with a sequence inside L2 mu that's a dextrodual to En. And the reason we call it a dextrodual is that the En system would not have any good frame properties, but a dextrodual would be a system of functions for which you get such a well-defined kernel here. And if you can do that, then that kernel would then be a solution to the K mu problem. In other words, that kernel would have the factorization property coming from integration of the boundary values with respect to mu, which is what the last equation here is saying. So this is a tool for getting factorization that's a little more general than the one I mentioned in the previous theorem. Okay. And I already mentioned that in principle, you could imagine maybe some cases where M of K might be empty. Probably for we could figure that out, but here we'll concentrate on cases where it isn't empty. And so here's some tools for getting your hands on it. Take your favorite closed subspace of the Hardy space and let K be the corresponding kernel. And then if the corresponding subspace generated by the backwards iteration of the backward shift is not all of H2, then you can generate lots of mu's in N of K. You can generate one for every inner function B, so that B0 is 0, and it follows from the earlier theorem. And so I'm not going to do it. But what I'm going to do with this one here is a little more detailed analysis of iterated powers of an inner function. So know that an inner function gives you a mu, but powers of inner function also inner function. So you get a sequence mu n like this. And so we want to study the properties of such a sequence here. So the mu n's come from a single inner function B here. So the theorem here is a little technical. I really don't have time, but I'll try. So you can rotate an inner function, and then you by going around some number of times with a rotation in arithmetic progression inside the circle, and then you can average it like this. But if you rotate the inner function, that gives you a new singular measure, and the corresponding family of singular measures would be mutually singular and so on. So this average here would be a singular measure, and you can compare that to two of them, M and N, where M and N are related this way here. M is a factor in N with quotient Q. And so our theorem is that if any two of them is in MK, then the others are as well, then the third is as well. So it gives you some more concrete ways of constructing measures in M of K. So I'm probably close to out of time. I wish I wasn't. The next one here is generating these kind of kernels as a double indexed family of coefficients. So we think about that as an infinite matrix C, and obviously it's a matrix must be positive definite in the sense that it generates a positive operator in L2. And so we want to study when we can get mu belonging to M of KC for some choices of infinite matrices C. And I'll be concentrated on the case where the C's are matrices for bounded operators in L2. And we have quite a few theorems about them, and I don't have very much time. But punchline is the following. You take one of your infinite matrix C, and then you take the corresponding gram matrix calculated from L2 of mu. And so you have two infinite matrix. You have your C and you have the corresponding gram matrix. And so our basic theorem is that you can get mu to belong to M of KC if and only if C satisfies the equation C equals to CMC. However, that equation is tricky. That equation must be made precise with the use of our Abel summations. And so we have a separate paper on how to do that and the theorems. And here are just some of the theorems that deal with this. One natural question you could ask yourself, when is the Lebesgue measure in M of kc for some C? And the answer is if and only if C is a matrix of a projection, if and only if the corresponding linear span of the kernels have the same norm coming from the KC kernel and from the Hardy kernel, if and only if the GN functions we talked about arise as a direct projection of the monomials, as he said, to the n. And in that case, the C functions would be like this. And so that's one of the theorems. And the other one is the one that applies to the subsets of the positive integers, including 0 here, that also describe the Cantor spaces here, the 3-Cantor and the 4-Cantor. And, for those, we have that Lebesgue, that we have absolutely continuous measures in these MK spaces. In particular here, we have these two gammas here. This gamma 4 has the differences of gamma 4 from points in gamma 4 is actually all of the integers, and we can use that to show that. Oh, okay, so we already know that mu 4. Oh, no, I'm sorry. No, that's the one with 3. No, the differences between points in mu 4 is not equal to the integers. So we get that mu 4 is in M of K4, but the Lebesgue measure is not. The differences between points from gamma 3 is all of Z. And so we get that Lebesgue measure is in M of K3. And then we have another theorem that shows that the only measure in M of K3 is the Lebesgue measure. So that means that this lacunary set of frequencies by powers of 3 would not do the job for the spectrum of any of the fractal measures like this. The kernels that we create this way here cannot have two non-zero terms in the diagonal kernel cannot have two non-zero diagonal terms. So in particular, this one here would not have any lambda in its MK because you have, so this is the Bergman kernel. And so this one here is the one that makes precise a solution to the equation C equals CMC, where you deal with infinite matrices and have to be careful about your Abel summability. And this one here is the one that says that you have a Lebesgue measure in M of K gamma here, if the differences is all of Z, so in particular for gamma 3, but not for gamma 4. But gamma 4 still has many absolutely continuous measures in M of K4, and including the ones that I'm studying here. But I think I'm out of time, so I want to thank you for your attention. I hope it was okay, and thank again. And so I guess I'm pretending I'm doing a symbolic bow, and thank again.
Thank you, Palle. Thank you so much for a great and exciting talk. Thank you very much. I clap on behalf of everyone who is muted at the moment.